Full text search. So this is one of the topics that every developer encounters once in their career, but very few actually understands it deeply. So in this video, we will cover what full text search is, the complete pipeline behind it, the different types of queries it supports, what relevance scoring is, how it affects this search engines, and real-time comparison with the PostgreSQL, MongoDB, and two search engines which are built for this purpose, which is Elasticsearch and Apache Solr. So let's get started. So the most classic example which I can take for explaining what full text search engine is would be the website of Wikipedia. So whenever you visit this Wikipedia website and let's say we search Java, it gives me all the suggestion which does not necessarily matches with Java. So it also provided me JavaScript and Javanese language, which is some language, I don't know. But it did provide me the suggestion. And if I write Java programming, it gives me weird suggestions as well, like Java and Frogmouth. I did not actually type anything like Frogmouth, but it did give me the suggestion because we have the word of Java. So this is an example of the real implementation of this full text search engine, and this is what it is. So whenever you search anything in your search bar, it gives you suggestion of words which are matching with your suggestion with your input word. So it does not necessarily have to be completely matching. It takes some score and give you the suggestion. And what is that process where the scores is being assigned is something which we will see in this video. You might have heard the like operator into the database world. So what like operator does is it basically search for any word which is matching to that particular word in the list of documents which you have saved. So it is very much similar to the full text search, but is it actually similar on behind the scenes? So we will see into this video. So here we have a comparison between the like operator and the full text search. So it's very important to know this difference. So in like operator, it basically checks each of the rows in your database. And let's say if you have 1 million rows, and by the way, we will actually see this live running into our database. And I will give you a walkthrough of how much time does it take and the comparison between both of them. So yeah, and the second point is it does not have the linguistic awareness. So if you are searching run, it will not show the result of ran. It will show the running because run is present into running, but will not show ran because it's a past tense. And on the other hand, if in the full text search, it will also show ran, run, runs, whatever matches with that particular search which you have made. So no relevance ranking. So if there are like 10 documents which are matching with run, it will not show it in the order it has to be. So if running is, let's say, integrated into the database before run, it will show running, but the exact word is run. It should be showing first, right? But it will not. On the other hand, full text search has that support of showing the relevance depending on the word which you have searched. So this is O of n complexity on your database. 1 million time it will compare. So and in the full text search we will be using indexing, due to which it will not search all the rows. So it saves a lot of time if you have large databases. So let's see it in action. Okay, now let's quickly compare the full text search with the like operation in real time. So we have this database where we have fill big table and it has 1 million rows in it. So if we simply run the like operation, so it takes 111 millisecond, and this is how the query looks for the like operator. And if we go on to the full text search approach, so we first have to create an index into the column. So it's already existing, so it will show already exist. And if we search it using this approach, it only takes 0.054 millisecond, which is a lot of improvement if you have large databases like this. Okay, so let's see the complete pipeline of this process. So whenever the text appears from the search field, let's take an example, the quick fox ran. So it in the further step gets tokenized. So tokenization is nothing but splitting the words into the array format. And in the same step also happens the normalization. So if there are any uppercase value, let's say quick is in uppercase, so it will convert it into the lowercase and the same format for all of these values. So the will be converted into small case. And in the next step is removing the stop words. So this step is basically removing the words which are not required into the sentence. And the next step is stemming, where the linguistic approach is being taken, and if the word is ran, it will also match the values of run. This step is called stemming, and the very important step is the inverted index, and here is the magic which happens. So in you might have seen in the previous example, what like does is search all the rows, like millions of rows, but in inverted index, if we search the word as quick, it will already have the mapping done to the documents which are matching. So let's say we have millions of rows and only 3 rows are matching this quick keyword. So it will not scan all of the million rows. It will just go on to these 3 documents and return it. So this is the complete magic which happens in this step. And the very last step is the relevance ranking of the relevance score. So BM25 is nothing but a common um, approach or method which is being used. So in this, there are multiple steps as well. So first, the term frequency is being checked. So how often the search term appears in a document. So how often does quick appear in these 3 documents. And second step is to the second is inverse document frequency, how rare the word is across the data set. Okay, so how rare is this quick word appearing in these 3 documents is also something which is being taken into consideration. And last is very long documents are penalized, so they don't dominate results simply because they contain more words. Okay, so let's take an example that document 1 has the word quick 10 times, document 2 has the word quick 1 time, and document 3 has the word, let's say, of quick as 20 times. So even if this appears 20 times the word, but if this paragraph is too big, let's say 1000 words in that, but the sentence in which the quick appears only 10 times, and the sentence is also like 20 words long sentence. So the ratio of the total words versus the number of times quick is appearing is very much large, right? So quick is appearing 10 times and the total words is 20. So the result will be shown where this document 3 is at the very top, and then the sentence where 1000 words are there but 20 quick is appearing. And lastly, let's say this only has one quick keyword, so it will appear in that order. So this is how the ordering is done, and this is like the complete conditions which we take while matching or while sorting the order of all the matching words. Now let's see the types of query, the way we search the words. So it basically is 5 type, but not all are important. So exact phrase is when we search machine learning, it shows all the documents which has machine learning, and the order is very much important to match the words. So learning cannot appear before machine. So next is boolean. So if you search quick and fox, so it will give all the sentences which has both of these words. So this is the boolean type. And wildcard is something where you just type micro, but it will show all the results of microservice, microbiology, etc., which contains the word micro. Next is fuzzy search. So it what it does is it will leave the option for showing the result which has the closest matching word. So we notice how we search just elastic, but it shows elastic search. This is how fuzzy search works. And proximity is it's not as important. Like the search and engine should appear in approximate 5 words distance. So search and engine should be in next 5 words, not as important. Okay, so here's a quick benchmark comparison between all of these four data types, not the data types, but the search methods. So this is from one of the research papers which I found online, and here is the comparison for exact phrase matching. The clear winner are the two services which are made for the search engines, and it's pretty surprising how these are like 100 times faster. And boolean and search is a place where PostgreSQL surprisingly wins. And the wildcard search is also where PostgreSQL is the fastest. And these are not quite far than PostgreSQL, but MongoDB is something which is quite slow in all of these matching um, mechanisms. If search is the main feature of your software, you should surely go with Elasticsearch and Solr, because Legion Search is implemented at the back of it. So Legion Search is something which is built, which uses all of these pipeline phases, and it's being optimized for that sole purpose since last 20 years. So don't get this wrong. Even PostgreSQL and MongoDB follow this pipeline, but the optimization which Legion engine has is on a whole another level, which makes these engines quite compatible for the searching purpose. And there are also different reasons in this. So phrase search at scale. So these engines are made to use on a large scale, and so even if you have millions and tens of millions of rows, it will use horizontal scaling, it will have cluster sharding implemented to it, and it will give results in milliseconds. So consistent speed, any size, search is your product, NLP, facets, and autocomplete. So it also provides these features to autocomplete whatever you write, and these two as well. But the situation changes when search is just a feature in your large application. You can use PostgreSQL for the same. So if your backend is already integrated with PostgreSQL, you don't need to um, set up a complete search engine if it's not the core usage of your application. You can simply integrate the gen, which is generalized inverted index. I'm not pretty sure, but it is what PostgreSQL uses behind the scenes, and it's very much compatible for the Boolean task which we saw. And the benchmarks are not pretty bad for PostgreSQL as well. So Boolean search and wildcard search is done at a very good level in PostgreSQL. If you already have integrated Postgres as your backend, search is a feature, a small feature of your large application, and it is something which PostgreSQL also provides things like ACID transactions, which search engines may not provide, because there is a scenario in search engines like when there are multiple clusters, it can have inconsistency when you delete one part of your table. So let's say you delete a few rows, so it may not consistently reflect in all of the clusters. So I can create a separate video related to it, but yeah, it's not very consistent, and PostgreSQL is better in this case. So you could use PostgreSQL when you have rows in low million of counts. So MongoDB is dramatically slowest than the other engines which we saw, and the sole reason for it was that in MongoDB there could only be one text index per collection. So, for example, this is a complete one collection where there is name, description, category, brand, and reviews as the properties. So you could only have index in one of these fields. So, for example, if you put index on name, you cannot have index on description, category, brand, and reviews. So this makes it very much slower compared to the others. But if you want serious search engine and your application is heavily integrated with MongoDB, so you can search something as ElasticSearch. So this uses the same Lecune engine behind the scenes, which the search engines use. So it will be comparatively very much faster in that case. All right, so this is the end of this video, and I hope any doubts you had about the full text search or anything which you did not know, you got to learn something new in this video. And it is not just another like feature. Search engine is itself another whole architecture where we saw how there are different steps built around like the tokenization, inverted index, linguistic processing, and relevance scoring. So yeah, if the search is your core product, consider using specialized search engines like Elasticsearch and Solr. And if it's just a part of your application where it's a feature like search, and if your backend is already integrated with PostgreSQL, let's say, so you could use Gin index, which we saw, which had comparatively close benchmarks than the search engines. And if your database is heavily integrated with some non-relational database like MongoDB, so do check the implementation and don't go with MongoDB's inbuilt search engine. But if you want, you could explore Atlas Index, which Atlas Search, which you could use with MongoDB. So yeah, that's pretty much it. And do let me know if you have any doubts in the comment section. And if you have come this far, do consider subscribing and liking the video. Thank you so much for watching. Bye bye.